So we're going to start with a tutorial on the physical vapor deposition system, PVD. The way that this system works is you have a vacuum chamber here with metal sources at the bottom, and you have a couple different ways that you can heat up these metal sources. But to start, you first have to vacuum it down to a very high vacuum. The reason being is the normal pressure forces when metal gets heated up keeps it in a solid or molten state. However, at a high vacuum, those pressure forces are a lot weaker. And as you add energy to the system of the metal source, it excites the atoms and is able to overcome any pressure pushing normally into the metal source and allows the metal to go into the vapor phase. So to do so, you first have to vacuum this down, usually overnight. This is a couple-step process, which you can observe happening on the... oh, man. So if I were, we'll just say we're going to stop this so that you can see it happening from the start. So what I've just done there is I've pressed the auto stop button. This is going to now vent the system, and I'm going to show you how this kind of works when you start up the vacuum system. So if you see here, as soon as I pressed auto stop, it opens up this vent here. So you have these four indicators to show which valves are open. This one right here indicates that the valve to the nitrogen air is now open, meaning that the nitrogen air is now purging the vacuum chamber, allowing it to vent. Before we open it up, well, actually, should we just open it up first? Yeah, since we're already venting it, I might as well. Let me show you what it's like inside. Yep. So this usually takes about a couple minutes to vent. Basically what it's doing is it's filling this entire chamber with dry nitrogen air. And if you feel along this seal here, you'll actually be able to feel some of that air coming out. Now when you're lifting it up, it is very heavy, so just make sure you're careful with it. So here's what it looks like on the inside of the chamber. We have a couple parts here that are of note, starting from the top. Right here, you have your quartz crystal counterbalance. This is how you're able to sense the thickness of metal that you're depositing and the rate at which it's being deposited. You also have here your rotary motor, your planetary motor. The reason why we have this is to spin this rotating stage here that the samples are attached to. This is so that if there's any hot spots of deposition, they're equaled out along the all of the samples. So if you take this out, you can see we have this set up right now to mount 4 different sample stages. So something like one of these. Basically, you can screw it right on, and then it's kind of holding your samples at an angle above your metal sources. So once you have your samples attached here, you can deposit them. So if you look in the chamber, down there we have a shutter. This blocks off the metal from being evaporated too soon. We can control when the metal is actually being exposed to the samples. Now, you can manually open the shutter here, open and close, using the shutter 1 toggle. If you leave it at auto, it will open and close according to the recipe, which we'll go over after we go over the main parts. So if you look down into the chamber, you can see right here is where you would put your resistive coil for resistive evaporation. Looks something like this, though this one got damaged and stripped. We have several more of these in cabinet over there. Basically, you put your metal pieces into a resistive ceramic-coated coil here. Through inductive and resistive heating, it heats up the metal, and that goes into the molten state. So in this case, we're adding energy to the system of your metal source via heat energy. Alternatively, we can also add energy to the system of the metal through electron beams. So inside this chamber, we have an electron gun. It consists of a tungsten tip and a heating filament. So the way an electron gun works in general is you apply a very high voltage across a emitter tip. This is able to pull out an electron beam from the very sharp tip of the emitter. And then we just aim that electron beam at our metal source. So you look down here, this is one of our metal sources. We have a 4-way carousel on this that rotates. So right now I've switched to the silver. Oh, wow. As you can see, the silver there got a little bit burnt. So in here we have oh, wow, yeah, that's the crucible, actually. Right, yeah. So this is another one of our sources. We can do up to 4 different metal sources. And basically what we do is we shoot our electron beam directly at our metal sources. Oh, that's not good. That's actually pretty bad.
What do you have?
It's stuck. See that?
Oh.
Yeah. We good? Right. So, now that we've made sure this is moving properly, what we have in here is we have our E-beam metal sources. So what we do is we take our electron beam, we fire it at our metal sources, and similarly to what we do with the heat energy and the resistive heating, we are now adding energy to the system directly by adding electrons to the system. And at the end of the day, what happens is it heats up and it goes into a molten or subliminal state. However, depending on the type of material, it may be preferential to do resistive over E-beam or vice versa. So, for example, gold electron beam coated has a tendency to form nanospheres, just because of the way that the grains form when you use an E-beam to add energy to the system. So if you want a nice smooth film of gold, you'd instead do the resistive heating. So that's something that's kind of material dependent. And what you'd have to do is you'd have to kind of look at the literature and see what results in what, essentially. So that's kind of all the parts that we have in here. I'm going to put our sample stage back in, and say we do a test wafer, right? Find a plain silicon wafer piece. Right, so what we're going to do here is we're just going to mount a plain silicon wafer onto one of our wafer platforms. First, we screw it on with these clips, kind of holds it in place so that, you know, if we hold it upside down, it stays in place. Then we're going to attach it to our stage with one of these Allen screws. We got one of these, and we're just going to screw it onto the mount. Very good. We have our wafer mounted. Now we're going to invert it, place it in this rack. So as you can see, this mount can rotate. Again, as I mentioned, this is so that we can avoid any hot spots and deposition within this chamber. So basically this bar right here catches on this rotating motor, making it so that it rotates. So we're going to go ahead and close our shutter. We're going to close our vacuum chamber. And then we're going to press the auto start button. So as we press the auto start button, you can see right away that the vent valve indicator has turned off and the roughing pump valve indicator has turned on. This is basically a diagram of the vacuum system. You see, this is your chamber. This is your turbo pump. These are your two thermocouple gauges indicated by here, TC1 and TC2. And then here's your ion gauge, which is on the right side of the system. It kind of looks like a light bulb. But as you can see right here, the chamber is now directly connected to this line, which connects it directly to this valve, opening it up to the roughing pump. So the way that these sorts of vacuum systems work is you first rough it down to a low enough pressure before you engage the turbo pump. The turbo pump has to operate at a lower vacuum. So before the turbo pump can turn on and start going to a high vacuum, first have to get it to a low vacuum with a simple rotary pump. So this is going to take, you know, around 5-10 minutes to get down to enough pressure for the turbo pump to come on. And then it's going to take a few more minutes to get down to a low vacuum. So somewhere around 10 to the minus 5, 10 to the minus 6, somewhere in between there. To get to a higher vacuum, it's going to require overnight. The reason being is These pumps are able to pump down from a high pressure to a kind of low vacuum very quickly, because all they're doing is they're sucking out all of the air from the chamber. Once you get to a higher vacuum, absorbed gases on the sidewalls of the chamber start to be leached out from the nanopores on the side. These gases are leached out, and then more slowly they're pulled away with the turbo pump. And that's why it takes longer to get to 10 to the minus 6, 10 to the minus 7 versus 10 to the minus 5 to 10 to the minus 6 torque. In the meantime, we can kind of talk about, I guess, some troubleshooting stuff. No? Okay, never mind. You can pause it. Right. So while we wait for the vacuum to get to a high enough pressure or a high enough vacuum, we can go over how you program a deposition cycle in this system. So in this system, you have up to 6 programmable films and 8 programmable processes. So a film is a single film deposit of metal, and then a process is up to a sequence of 4 of those 6 films. So for example, if you wanted to coat gold onto a wafer and have it well adhered, you would have a process that starts with a adhesion layer of chromium, and then a second film would be your gold deposited. Basically, it's a 2-step process, and your process can be up to 4 different steps. So the way that this works is it's all pre-programmed for the E-beam usage. For the resistive usage, that's manual, but we'll go over that in a moment. So we'll start with all the different different parameters that you can set to do your recipe. Essentially, what you do is you first heat up your metal source at a slow rate that won't damage the gun. You heat it up to a point where you are outgassing any contaminants from the metal source. You lower the heat so that you're not depositing metal too quickly when you open the shutter. And then you open the shutter, and a feedback system basically does feedback so that the rate is to the set point that you put it at. So I'm just going to go over that, what each one of these parameters means in relation to that recipe. So the first one here is rise time. The rise time should be long enough that it gets to your soak power, but not too quickly. You don't want to go like immediately from 0% power to the gun to making your metal into a molten state, because you could damage the gun or induce thermal stress at the source, which could shatter your crucible. So this is usually around 2 minutes is a safe amount of time to get up to your soak power. Next come your soak time. The soak time is how long you heat your metal at an to the point where it would be molten or subliminal to outgas any contaminants. So right now I have this set to 10 seconds. Anywhere around 10 to 30 seconds, you should be outgassing any contaminants from your metal, making sure that you have a pure metal film that's deposited. Next, you have your pre-deposit time. The pre-deposit is where you lower the power from your soak power to your pre-deposit power. This power should be low enough that it's not completely making your metal source molten or subliminal, but it should be high enough that it's still well heated so that when you open up the shutter to deposit, it's not going to be completely experiencing thermal stress by changing the power to the gun too quickly. So essentially you want to lower this, again, as I mentioned, so that you don't deposit your metal too quickly right when you open the shutter. So that's why you do it. You want to have some control over how quickly you deposit the metal. The set point is an exterior set point that you can connect to some sort of exterior circuit. So if you have some other thing that has to happen at, say, 5 minutes, it will send a signal, which can be accessed from the back panel of this system at 5 minutes. If you don't have an external process you have to do, then you don't have to worry about these set points. But there are a couple different set points that you can use. Next, you have your soak power. So a good soak power is somewhere around 16%. And in general, when you're determining what the power should be, it's going to be trial and error. So essentially, if you're doing a new metal source, your soak power should be at the point that your metal is completely evaporating, or rather, not completely evaporating, but you can tell that it's molten or subliminal and it is evaporating. So that's that's a high enough power that it's going to be outgassing any contaminants. Your pre-deposit power is slightly lower than your soak power so that you're not depositing metal too quickly right when you open the shutter. The max power should be somewhere around 30%. That's just what the electron beam in general here can handle. And this is kind of a safety thing to make sure that you're not damaging the system. The idle power kind of depends on what you need. The idle power in general could make sure that there's always some amount of power delivered to the metal source. This is most important between different steps of your process where, maybe you're doing, pre-deposit at some certain level. You want your idle power to be some percent so that it's like staying hot. However, if your process doesn't call for that, you don't have to put anything there. So right now I have it set to 0. The rate is in angstroms per second, and this is how quickly you're going to deposit metal over your source or over your sample. Right now I have it set to 1 angstrom per second, which is the lowest you can get. You can set it to anywhere up to about 20 angstrom per second. Past that, you risk damaging the machine. Here's another set point. So this is now a set point that sends a signal when you get to a certain thickness in kiloangstroms. So this is set to 8 kiloangstroms, but there's nothing connected to that signal. So again, you don't really need to worry about this too much unless your process calls for it. The thickness in kiloangstroms is how thick of a metal it's going to deposit before it closes the shutter. So right now I have this set to 0.02 kiloangstroms or 2 nanometers. And this is why I had such a slow rate, is because I'm doing such a thin film. I don't want to overshoot my target thickness. Source and sensor. This connects the crystal counterbalance in there to this system. It should always be 1-1. We only have one crystal sensor and one connection to it. So this should always be 1-1 so that you're properly connecting your sensor to the system. The response controls how quickly the feedback occurs. So essentially, you have your rate set point that you want it to be at, and you have your power. If your rate is below the rate that you have set, there's going to be a feedback response that is going to increase the power until it reaches that rate set point. So this is a percent, basically, of how quickly that feedback response is going to occur. So right now I have it set to 20. That's a good kind of gentle response setting. If you wanted to respond more quickly, you can, or more slowly. It kind of depends on how concerned you are with thermal stress at the metal source again. The error limit just determines what percent error of the rate or power that it can have before it shows you excess error on the trouble sensor. Basically, this is just how much error you're allowing, or how much is within tolerance for your rate. If it's too far from it, it will send a signal to the excess error, and it will show that to you. The tooling percent is kind of a mathematical relationship between where the substrate that you're coating and the sensor is. So as I showed you, the sensor is at the very top of the chamber, and the substrate is a little bit lower than that. And then you have your metal in the same spot at the very bottom of the chamber. So basically the deposition happening at the very top of the chamber is going to differ slightly than where your samples are. So there is a mathematical equation that relates the distance between the source and the substrate, and the source and the sensor, that can determine exactly what this is supposed to be. Right now we have it set at 100%, but if you would like to go in more depth into it and actually do all the measurements, you can do that, take measurements of the chamber and see exactly what it's supposed to be. Up next, we have material properties of the metal that you're using. So the reason why you have this is because, again, we have a crystal counterbalance sensor. The way this works is it's a quartz crystal that oscillates at a certain frequency when you run a current through it. As you deposit metal over this crystal, that frequency is going to change. So interiorly, this does some math relating the density of the metal and the acoustic impedance of the metal to the known area of the crystal and then it's going to output a thickness and a rate. So basically, these are material properties that are different for every metal source, and that determines how it does the math to figure out how much metal you've coated over your sample. The other stuff here is mostly feed and interlock. These all have to do with exterior outputs that you can do, program in certain ways. The feed stuff has to do with the feed between one film and another in a process. So for example, if you have a feed time, that's how much time you have before you switch to, say, like I said, you're doing chromium and then you're going to do gold. So if you put a feed time of 1 minute or so, that's how much time you have to set up to switch over to your gold deposition from your chromium. You can set this to whatever you want to make that most convenient to you, but that's what it means. And additionally, you have a feed power. So if you want to keep your sample heated during the feed, you can do that. Finally is the crystal health, parameter 36. This determines when you should change the quartz crystal in the counterbalance sensor. If this is below 85%, you should change the crystal. And that's all of it. Once you have all that determined, you just set your process that you want to do. So if you do set process 1, set process 1, there we go. It's going to do the process number 1. If you want to show what process 1 is, whoops, oh, that's not good. Okay. You show what process 1 is, it's a film sequence of film 1 and 4. Film 1 is chromium, and film 4 is silver. That's just how it's set up. We use process 1 for chromium and silver. If you're just coating chromium, basically you would stop at the feed between film 1 and 2, or in this case, film 1 and 4. If you want to show different film recipes, so if we want to do film 1, this is the recipe for chromium. If you want to do film 4, this is the process for silver. But right now we're just going to do film 1. All right, yeah. So this is the process for film 1. Once you have the process set and your recipe set, at the point where you're actually going to deposit, all you have to do is start up the beam and press start, and it'll do it all automatically. And that's pretty much it. Oh. Oh, it didn't record? Are we doing which part? This one? Okay. Yeah, so what we've done now is the vacuum system has switched over from the rotary pump to the turbo pump because it has reached a low enough vacuum here at thermocouple 2. So you have these two set points here at 30 Pascal and 1 Pascal. So once the mechanical pump gets the chamber down to 1 Pascal, it will switch over to the turbo pump. This valve closes, this valve opens, and this valve opens. That way now your vacuum system is going through your turbo pump out to your mechanical pump. If the pressure for any reason rises above 30 Pascal, it's going to do the opposite. So it's going to close both of these and open this one. That's what those two set points determine. Yeah. So we have the most important set points here as far as the switching goes are the two set points for thermocouple 2. Thermocouple 2 measures the pressure in the chamber. When the pressure in the chamber reaches 1 Pascal, 1 Pascal there, it's not holding it, but yeah. Once it reaches 1 Pascal, it closes the valve to the mechanical pump and opens the high vacuum valve to the turbo pump, as well as the valve past the turbo pump. If for any reason the pressure or the thermocouple 2 reads a pressure that is greater than or equal to 30 Pascal, it's going to close these two valves and open up this valve. So that's how the automatic switching works. If for any reason the power goes out in the building, it's possible that these set points will be reset. These set points are recorded on the operating procedure and on the website, so you can always reset all of them. Additionally, here we have set points to the ion gauge. The ion gauge set points are the points at which the deposition will turn off. So if the pressure rises above 10 to the minus 4 torr while you're doing a deposition, it will automatically shut the ion beam or the electron beam off. So that's just something to consider, and that's the reason why you want to get as low of a pressure as possible, because as you deposit metal, this pressure will increase a little bit, and if it goes above 10 to the minus 4, it will just stop your deposition in the middle of it. Additionally, we have a couple other buttons that are of note here. So this is how we turn the filament for the ion gauge on and off. So right now it's on, now it's off. And you can see that operating from the side there. If you take a look at the side, you can see that you have the ion gauge. It kind of looks like a light bulb there. So right now it's on. Whoops. Button's a little tricky. There we go. So right now the gauge is off. I'm turning it back on. You see the filament lights up. So that's how you can tell if the ion gauge is working. I have a couple other things here. So we can change the units. Right now they're in torr. You can change them to Pascal if you'd like. But in general, we'd like to keep it at torr because everyone's more used to that. There we go. The final thing, if you have to change it, oh no, sorry. So if you have to change the set points, these are the buttons that you change it. This ramps the set points up and down when you hold down the set point button. Additionally, do not touch the ion tube button. Reason being is this controller is kind of old. What happens if you touch the ion tube is it tries to switch to a second gauge that does not exist, and it errors the whole thing out. If for any reason you accidentally touch the ion tube, you'll have to unplug this controller and let the capacitors discharge over time, about 15 minutes. But as long as you don't touch it, you should be fine. And I think that's it for the ion gauge controller. Additionally, on this panel, we have these main circuit breakers. We have the main control, circuit breaker to the mechanical pump, circuit breaker to the high vacuum pump, substrate heater, which our system does not have, and then auxiliary, which connects to the resistive heating component. Finally, down here, we have the controller for the turbo pump. Right now, you can see that the power is on, and it's in normal operation. If the power goes out, or if there's something wrong with the turbo pump, it may go into a failure state or just turn off. In that case, you would press the start button to restart it. Under normal operation, it should show the acceleration indicator until it reaches the set rotation speed, which will then go to the normal operation. Same way, if you want to stop your turbo pump, you press the stop button. It will maintain power to keep everything running properly as it slows down the turbine, and then we'll finally come to a stop. So that's how you basically start and stop the system. And I think that's most of it, yeah?